Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Surface Drainage, Roads and Shared Spaces. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to them and their cultures and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar has been hosted with Engineers Australia's industry partner, Echo Pty Limited. Echo in Australia offers an extensive portfolio of stormwater, building drainage systems, cable pit and ducting systems, access covers, and other niche products. The company has just celebrated 25 years as Australia's foremost manufacturer, with facilities in Western Sydney, New South Wales. Echo takes pride in providing excellent customer service and extensive technical support from specification through to the finished product installation. Today we will hear from two speakers followed by a live audience Q&A, and I encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Alan Roxy. Alan has over 16 years of experience working on a variety of water and infrastructure projects, both in Australasia and the UK. Alan is currently co-leading the Arab Stormwater team in Brisbane and is leading the stormwater design on projects in Queensland and New South Wales. Alan has extensive conceptual and detailed design experience in drainage design on both minor and major road projects, using a variety of standards. Please welcome Alan Roxy.
Hi, and thank you for that introduction. Welcome to the first presentation on stormwater trench drainage today. Before I start, I'd like to give an acknowledgement of country from where I am based. So I'd like to acknowledge the traditional custodians of the land on which we're meeting today and pay my respects to elders past and present. I acknowledge and respect their continuing culture and the contributions they make to the life of this city and beyond. So, stormwater removal. It's worth noting that most people only start thinking about drainage once it's not working. If it's been blocked, if there's both on the surface and underground, or if the system is surcharging, which you can see in these photos. There's a number of reasons you can end up with a system that doesn't work. All of these, I think, in the pictures I've shown, they are not working, and it's not because they've been poorly designed. There's been something additional that has caused the problem. You can design for your set storm, and then if the storm gets bigger than that, it'll fail. You can have additional blockage. So just because something looks broken doesn't mean it's not doing exactly what it's meant to do. Some things are unfortunately meant to flood. So the traditional way of looking at stormwater, if we take it back to basics, we are looking to get water away from where it's currently falling, be that a road or a pedestrian area. So in a wide open space on a new road, we can just let that water sheet flow over the edge and away. We don't need to think about it any more than that. As areas get more built up and urbanized, you may need to capture that water as it flows off the road in a grass swale. That's the simplest and most basic form of getting drainage away after it's landed. As areas get more constrained beyond that, you might need to put a hardline swale in that resists the erosion that might happen, lets you concentrate the stormwater and move it away more quickly. There's a number of other ways you can get drainage away, but that is the basic, cheapest, simplest way to do it. And then when you move on beyond that, because things are more urbanized, you want to put a footpath next to the road, you need that next traditional drainage, pits and pipes. These are used everywhere in urban spaces where space is at more of a premium. And in their basic form, you put a curb and channel at the edge of the road, you let the flow go across to the channel and build up. Once there's too much flow at the edge of the channel, we put a pit in and let it flow into a pipe and away underground. And that works just fine. Unfortunately, as cities have grown, that lane at the edge of the road that's being used for stormwater wants to be used for other things. It could be parking, it could be for another traffic lane. And then we need to find a way of getting the water away without having it at the edge of the road. And obviously pedestrians are not great at walking through water, so we need to avoid them getting their feet wet. So the solution to that is continuous capture drainage. There are a few different ways this can happen. You can use a trench drain, which is what it says on the tin. It's a trench in the surface of the land with a grate over it. The water can go into that as soon as it gets there and flows away. Slot drains in the middle there is a pipe just below the surface with a vertical slot to let the flow go into it. Again, minimizes flow width on the surface and the flow can get away. Or a combined curb drainage, which is a hollow curb with holes in it, can get into the curb and disappear that way. So these are all similar but different in what they do. They all have their benefits, their limitations. The slot in a slot drain can limit the inflow of water into the pipe. It's quite easy for that to get blocked. Grated trench drains, I think everyone is familiar with. But if we put these in poorly designed, poorly thought out scenarios, we run the risk of them not operating effectively. So we have pros and cons. As I alluded to a moment ago, there's little to no flow width on the surface using them. We don't need to excavate much because they are very shallow. And they're very unobtrusive when well incorporated with the overall design. So they can be used all over the place, but they do have issues. The principal one is that they can fill up with silt, which means they need a lot more maintenance. And if they're not maintained, then they don't work. They may as well not be there. So we need to design to minimize that maintenance need. Water, the first rule of drainage is that it flows downhill. So you still need to get the water to flow downhill. If you put a trench on with 0 grade, water will flow in and it will build up and flow away, but it will do it that slowly that it's going to fill up with silt. So you've shot yourself in the foot. The grates above trench drains, they can be prone to blockage, which will limit their capture rate. And that's more of an issue as you get to pedestrian areas and you need to let flows in, but not have high heels get stuck in the grating. Then you have a grate that's small enough to stop the high heels, which means it will stop and capture more litter and debris, which will block the grate. Obviously, if you put them in the wrong location, they can give a negative impression. Then we go, what is the purpose of this? What were they thinking? The grate and trench obviously needs support as well. So you need to make sure it's properly incorporated and constructed. And lastly, although we said in the pros they need less excavation, eventually you still need to get the water that's in them out and into a buried pipe somewhere. It doesn't just magically disappear. You've got to get that away. So keep in mind, what are other options? Now, these are all solutions that do work, and they work by letting water pond to enter the system. And what they've done or had to think of in these areas is how do we do that without causing a nuisance to pedestrians? So at the top left, they've made the the asphalt going through the car park into a V, so the water will pond between the car's wheels, and that can then channel the flow and take it away. On the top right, they've made a series of sag ponds and put a grate in the middle there, again away from where the cars will park, so people can get out without getting wet feet. They've put raised zebra crossings, which will let pedestrians walk from one side to the other without getting their feet wet. And in the bottom right, you can see that being repeated in multiple locations because people don't need to walk on the right-hand side of the photo. All the access is on the left. And the bottom left is the outlet to that open channel. An open channel is great, but you still need to get the water away. That's a very unheal safe grate. It's huge, but that's an area prone to flooding, so they needed a big inlet to get the water away. As I said, all of those, you need to get water into an area and stop it, allow it to pond. If it doesn't pond, it will struggle to get into the grating. So in pedestrian areas, check your grating capacity, especially allowing for blockage, and the surface gradient. If you design something with no gradient, so at 0, it's okay, it'll build up, it'll flow away. Construction tolerance means you'll end up with ponds everywhere. As you get little depressions, they can't build to a perfectly flat surface, and even if they managed it, the land will settle. So adding a small amount of crossfall will let the water get away without ponding. So ponding depth, as I mentioned, it's good for capture. The more the water will pond up, it'll increase the amount of flow that can get into any inlet. But you can only really allow that to happen away from where pedestrians are going to be walking. So thinking more about inlet capture. So we've agreed there's areas where trench drainage and continuous capture drainage has its purpose. But if we're going to put it in, we need to think about the best way to get it in. And we can look at this in two ways. If your trench is in a low point, it's a sag, that's great. We can look at those two equations there, which is the orifice equation and the weir equation. We can include a blockage factor, which allows for debris getting in. We can also allow for blockage caused by the actual grate itself. So a heel-safe grate can close your opening up by 60 to 70% from just a basic hole. And we can use that. Blockage factors, generally we use 50% for sag inlets, but if there is a lot of debris around that when you consider it, there's a higher chance things will block, then you may need to use more than 50%. If, as we have in the top right or top left, sheet flow approaching the grating, we can use the equations in HEC 22, which we use for our standard inlets with lintels and grates. We can use them to make an assessment of how much flow will get into the grate as it arrives. It's worth noting these equations, they relate to an individual inlet. They're point flow capture equations, and obviously the trench is continuous. But for a first approximation, when you're starting to model these trenches to make sure they can go in the right location, they are perfectly adequate. Channel flow is the next thing. So we've got the water, we've worked out how big the grating needs to be to get the right amount of flow in without excess ponding. And now it has to flow through the channel and escape. And the flow in the channel is non-uniform because as you go further down the channel, more flow will get into it. But to do a quick check, is my trench going to work, or do I need to step back and have another think? We can use Manning's open channel equation to work out how quickly the water is flowing. If you use Manning's open channel for a flat trench, on grade is 0, velocity will be 0, it won't work. that is the limitation of the equation. Obviously, the water will flow away, but you'll need to work out how to get rid of the sediment that it leaves behind. A better option is to slope the trench, either by sloping the ground or adjusting the invert of the trench as you go along it. That will give you some gradient, which will increase the velocity and, again, help move the sediment, get rid of it. There is obviously an issue with that. The top of that trench had no flow, means no hydraulic radius, no velocity. So the sediment will build up. Once the sediment starts to settle out, it will increase the roughness, which will slow the flow more, which will help more sediment settle, which is a bit of a vicious cycle. The solution to that, if you can do it, and here's where you need to think more carefully about how you're designing, is there a way you can have some water build up on the surface before you start your trench? Or is there a way you can put water into the trench below ground from a roof water downpipe, for example, to add that kick right at the start so that you have sufficient velocity in a small storm at the start of your trench that the sediment won't settle out. Beyond that, there are other options you can think about to improve velocities and stop the sediment settling. Don't pick the widest trench possible and keep it shallow. If you pick a deeper, narrower trench, the water will flow more quickly. Obviously, when you get to a certain size, you will need a bigger trench. And directing overland flow, if we can get overland flow into the start of the trench, even if you say, oh, the flow is bad, it's going to cause a problem right at the start, the benefit to the client might be, but you won't need to get out and dig out dirt from the trench every time it rains, or before every time it rains, which is more of an issue. Capacity of a channel is not just to do with the areas we've talked about, the amount of flow in it, the gradient, the width. If it's poorly constructed, both in the channel or in the carrier pipe when you discharge, it's not going to work. It's going to slow down. This location I took a picture of, the trench actually looked fine. There was no sediment there, but there was a plant growing out of the vertical pipe where the flow left the trench. So there's something wrong with the trunk drainage below that, which is going to stop this from working. Other things you can use to improve velocities: egg-shaped inverts to a channel or a V-shape will concentrate the smaller flows, and that will increase your velocity and allow sediment to be transported away. The difference between flow capacity and self-cleansing velocity is a delicate balancing act. If you want to design your trench to work in the 1 in 1,000 year storm or the 1% storm or any significant storm event, then in the smaller 1 year or smaller storms you use to check for self-cleansing velocities, there won't be flow getting into it and it's going to fail. Thankfully, mostly trench drains, especially in pedestrian areas, won't be designed for anything like that large event, and that should help with the balancing act. Other things you can do which will improve channel capacity is to reduce the roughness. The smoother the channel, the more easily water will flow and sediment will move. Adding grade. We talked about slope channels. We talked about sloping the surface. Potentially you need to do both at the top of the channel, so you have a sloped channel on a sloped surface. These are all little tricks you can use to get your channel capacity higher and make it work better. So these are examples of poor installations. The channel in the top left is at the entrance to a basement car park. It has about 20 meters length of driveway falling down to it. So that's 200 square meters. And if you assume it's designed to capture flows in a 10% AEP event, that's around 10 liters a second, 17 liters a second in your 1% event, but only 5 liters per second in a 1 exceedance per year event that you'd use for self-cleansing velocities. That's all using ballpark figures. Obviously, you would need to check your actual rainfall intensities if you were designing this. To make things worse for that trench, the outlet is in the middle. So each half of the trench will take half of that flow. And although it's all turning up at once, that's not much. 2.5 liters per second in a trench that is about 200 mil wide with a flat base. As you can see in the second photo, it was just full of sediment, and that will need to be maintained, or the car park will not be protected by that trench. The next photo, channel or trench. Clearly, this wasn't well thought through. They've, again, has a small catchment. Half of it, they put a trench in. Half of it, they put a channel in the surface, which has then cracked, either poorly placed concrete or not well bedded, and vehicles driving over it have caused it to get damaged. But because that trench doesn't have much flow going to it, it's had flow settle out, and at the upstream end, there's plants growing through it, so it's just a glorified planter. It's not doing anything. And these are the issues we get if we don't have well installed and well designed infrastructure. Then clients get put off. They don't want to put things in that they believe are maintenance headaches, and you need to then work very hard to demonstrate they're not maintenance headaches. And the more things that are put in poorly thought out, poorly designed locations, the more they will be resistant to using them where they can be used. So moving on, we've got our water, we've got it in the trench. We've made sure the trench is big enough to take the flow and small enough to move the sediment along. The next thing we have to do is get the water back out of the trench. And when you stop and look into this, this quite often controls the overall capacity of the trench. There's a few ways you can do it. One option, which is the photo on the left here, is the trench goes into a pipe, and the pipe can then go to a pit or away elsewhere. That pipe is smaller than the trench. You've got losses getting into it, so it is going to cause the flow to back up, which is why in this instance the trench has been made a little deeper, just approaching the pipe to give some extra headwater. The second option is to punch it straight into the side of the pit, as you can see on the photo on the right. That's obviously a normal road pit. You can use any sort of pit as long as the pit's designed to have that hole cut out in the wall. The third option is to drop things vertically. So these are a quick high-level calculation to see how things are going to work. I treated the culverts, the outlets that were pipes going horizontally, as small culverts, and then I treated the flow in the channel. I gave it a 0.5% grade and just used Manning's open channel and said, well, what's the capacity of the channel? What's the capacity of the culvert? And the headwater for the culvert needs to match what the flow would be in the channel, same depth. Otherwise, when you put your outlet, what will happen is your full channel will back up and overtop. And I tried it in a 200 mil channel, tried it in a 300 mil channel. And in both instances, you had to drop your channel, make it deeper to get capacity to let that flow exit the channel into the main drainage system. The other option, as I said, vertical discharge. So we're not looking at this as a culvert anymore. So I should have said, if you're just punching into the side of a pit, the discharge issue goes away quite quickly because it will flow like a weir out of the pipe, out of the trench, and then it can go out of the pit in a normal way. The pit will be deeper, so it is doing exactly what we were trying to mimic with the short, deep section of trench. It lets the water build up and go away in the pipe. If you're discharging vertically, it is another equation, the orifice equation. And this can, again, cause problems because you have potentially flows coming from both sides, but the orifice equation that is the top one of those two it can be used to calculate how much flow will get in given your depth of channel. If the flow approaching is smaller, then the Weir equation that's below that will be more applicable. And so you look at both of these, and to be conservative, make sure we've got this correct, we pick the smaller of the two discharges. So given a 300 mil ponding depth, if your vertical pipe is 200 mil, you'll get 41 liters per second discharging through it. If your pipe is 300, you'll get 93. Obviously, the larger pipe has a much better discharge. So you may need to deepen the section approaching your discharge point there again, especially if the ground is getting flatter. You can do that by sloping your invert or just having a section of deeper pipe. I've talked a lot in this presentation about sedimentation, and a lot of the thought going into this is about solutions to help minimize maintenance, to remove sediment, and to design to provide a location where sediment is going to be easier to remove. These are both obviously not continuous captured solutions, but they both have sediment. You have a curb break going to a pit. The pit is full to the brim of sediment. The other one, there's a sediment forebay that's capturing sediment before it goes into a small fire retention behind the curb. So if you start thinking about this from a water quality perspective, people get upset that we put in a gross pollutant trap. It's a nightmare. It fills up with sediment. That's the purpose. Sediment will be there. Either we need to pass it off downstream to somewhere else, or we need to capture it. And you can't just keep passing it downstream into water bodies. So it does need to get captured somewhere, but the trench drain is probably not the correct place to capture it. So think for some other solutions to get rid of it. So in conclusion, trench drainage is a good solution if well thought out. If you give a stormwater designer a completed master plan of a car park, a pedestrian area, and say, now drain it, then you're likely to get poor solutions unless the person designing the surface has thought through where water is going to go. Can we corral the water into a certain location? In this photo, there's an open V channel. This is the car park I used at the start. And that water from the driveway on the right can't get there. It's being put into a trench potentially because of a development application constraint. But logically, that water should just have bypassed the trench, got into the channel, and away that way. So you need to think, you need to work together with the landscape designers, with the earthworks designers to get a solution. There's a pedestrian mall on a bit of a hill, but to increase the velocity in the trenches are on a diagonal angle going down the pedestrian area, so that you've got the slope of the hill, you've got the capture from it being partially across the hill, but they've increased velocity by just skewing it, and then worked with the architect to merge that into the paving so it works well. You can't design this as a one-man band. You need to work with everyone else to get an integrated design, or it's going to fail. Other thoughts about how to use it: you can use a trench instead of a lintel. This is on the inner city bypass in Brisbane. There was no space to put a lintel in when this was designed, so 2 or 3 meters of trench drain was used upstream of the pit to increase the capture, which works quite well as a solution, but it doesn't provide anywhere for leaves or debris to wash through into the pipes in a way, so the leaves and debris will continue going down the road. And that's the end for me, if there are any questions.
Thank you, Alan, for your presentation. I'd now like to welcome our second speaker, Greg Facey. Greg is the market segment manager for Echo and began his career with the organisation back in 2004 as Queensland Specification Representative, providing education and project solutions to many state authorities, engineering and architectural firms. Greg progressed into the current market segment role, providing education and CPD support, technical advice and design brief developed nationally to industry associations, transport authorities and designers in the stormwater management space. Please welcome Greg Facey.
Hello everybody, and thanks for joining today's presentation. My name is Greg Facey and I'm the Market Segment Manager for ACO. So in this presentation, we'll discuss the challenges with draining flat pavements in roads and shared spaces, with an emphasis on the features and benefits of surface drainage that must comply with Australian standards and regulations to ensure a safe passage for motorists, pedestrians and cyclists. So let's begin with surface drainage for roads. So looking at the modern drainage designs, we have a lot of challenges from our growing population. So as our population grows and cities become more and more densely populated, engineers are being tasked with designing effective road network and integrating the drains and other services into narrower and narrower road corridors, either to widen or reconfigure existing roads or extend or add lanes for turning bays at intersections. So beyond just trying to fit more into a small space, some of the other challenges include connecting to an existing stormwater system that can't cope with the increased flows from continual development, trying to avoid clashes with underground services. So the primary objective of road drainage is obviously to ensure the safety for all road users, whether it be motorists, pedestrians or cyclists, by reducing the depth and the width of flow on a project, but managing and reducing or eliminating sheet flow and the spread of gutter flow will minimise the risk of hydroplaning and vehicles losing control, and also slips, trips and falls from pedestrians as well. Surface runoff on roads is collected and channeled along curbs and gutters and along medians on super elevated roads. Inlet structures are used to capture the surface water and transfer it to an underground pipe system. And this could be at a low sag point to prevent ponding on grades before the water depth, width and velocity becomes a hazard to users, or at approaches to, say, intersections or upstream of pedestrian crossings, and also at bus stops where people tend to congregate. Now, there's three different traditional types of drainage inlets available, either side entry inlets through the openings of the curb face, grated gully pits which are positioned in the gutter through the grate, or a combination of the two with an extended side entry. But you can also capture water continuously rather than intermittently using graded trench drains or curb drains. And these will be used in areas that are traditionally very flat with minimal fall, or have surfaces in the ground that are close to the surface. And these continuous capture systems are more cost-effective solutions than installing closely spaced curb inlet pits and deep pipework. And we'll have a look at that in a bit more detail later on. Actually, Ausroads released the Guide to Road Design, which is in Drainage Section 2013, and it was written with a consortium of all state road authorities. And since this document was published, continuous capture inlet systems have become more of an accepted method of draining road pavements in certain applications. So now let's have a focus on continuous capture inlet systems. So graded trench drainage is one type of continuous capture inlets, and due to the rainfall variance in Australia, we tend to see 200 or 300 wide channels commonly specified, as they are compact with variable depths to ensure the runoff is discharged efficiently. There are generally three types of grates, either in a high flow with large aperture configuration, a hill safe for pedestrian safety, and transverse slotted grates. And graded trench drains must be low rated to AS 3996 Class D, and preferably fitted with a boltless locking mechanism, which allows quick access for maintenance to clean out the trench drain from time to time. Precast polymer concrete channels have a very smooth surface and are available with built-in slopes to further improve hydraulic capacity to remove water effectively from flat areas. Hydraulically, with a V-shaped channel profile, the channel creates a higher velocity during low flows compared to that of, say, a U-shaped channel, or even worse, a flat base channel. And this is due to the narrower V-shape at the bottom third of the channel, which creates higher velocities to promote self-cleansing to help keep the channel clear of debris and silt build-up and ready for the next storm event. So in precast channels, the V-shaped profile creates deep pockets in the sidewalls of the channel, which allows the concrete encasement to mechanically key in and around the channel for strong installation. They also have wide ribs to give the channel additional strength, which makes them ideal for these dynamic applications. And channels with ductile iron edge rails, rather than steel edge rails, provide a more durable solution. So edge rails with features such as anti-shunt lugs prevent longitudinal movement of the grates, and also shock absorbing widgets to help noise reduction with vehicles traversing over the grade, so you don't get that clunking noise. And there are a number of different ways to install precast channels. One way is to use installation devices, and installation devices clamp the connecting channels together to prevent movement, and they also stop the channel floating during the concrete pour. They also make installation quick and easy by reducing formwork and allowing installation to happen with a single concrete pour, so much more cost effective and also stronger installation. High flow grates have a large high capacity tapered inlet slots that are 80 by 75 mil, and each of these allows the runoff to be quickly intercepted and removed from the surface. And these large intakes also minimise the risk of grates blocking up and creating hazards to motorists with flow spreading into the traffic lane. And even though these grates do have large inlet apertures, they are bicycle compliant to AS 3996, which means that bike tyres won't get stuck in the grate, injuring a cyclist. These high flow grates have such a large apertures that allows the channel to be cleaned without the grate having to be removed. A sucker truck with a high pressure washer, for example, is used to break up the sediment and wash it down to the vacuum pump, which sucks up all the suspended silt into the truck. And this can all be done without unlocking the grates and removing any of the grates in the traffic carriageway. So it allows quick maintenance of the system. The next continuous capture inlet system I'd like to share with you is the curb drain. And this is really a great product as it combines the two functions, which is a drainage system with the curb itself. So it's a really shallow solution, which requires less excavation for the installation, therefore less likely to have clashes with any existing services. Options include semi-mountable and barrier type curb profiles, and depending on the specific area with the roadway. There are a number of wide curb drains which are ideal for minor roads in council areas and is a good compact size for minor catchments. Now, the 200 mil wide curb drains are for major roads and larger catchments. So semi-mountable curb drains are used in medians predominantly, and the barrier curb is used, which is a non-mountable option that is used adjacent to footpaths to stop vehicles from mounting the curb. So access units are generally required at regular intervals, so let's say every 20 or 30 metres to provide access for cleaning and maintenance. And precast curb channels are encased in concrete and tested to AS 3996 Class D loads. And here I'm just going to quickly run through some installation examples where graded trench drain and curb drains have been used along different parts of roads and highways. So for medians, they might be used to eliminate the spread of gutter flow into the traffic lanes by continuously capturing the water rather than traditional pit and pipe construction. A curb drain is a smaller system, so depending on the hydraulic capacity requirements of the project, wider and deeper graded trench drains might be a better option. And for right-hand turn bays, where we're trying to fit more lanes into a smaller area, curb drains can be a fantastic solution to give as much space to the roadway as possible. And some engineers and road authorities may prefer graded trench drains to curb drains for this application. And in curbside gutters where existing inlet pits are spaced too far apart, resulting in a hazardous spread flow, curb drain can be used continuously to capture the gutter flow to minimise any risk to motorists. Or, again, a graded trench drain solution can be used in this application as well. And of course, with all surface water management, we're trying to prevent damage to property and people, and curb drain can be used to intercept water upstream of lower lying properties. And likewise, graded trench drains can also be used. And also on bridge abutments and tunnel porters, you can use curb drains or a graded trench drain as a solution. So they're quite versatile products. Can also be used on bus stops and railway interchanges because they have a lot of pedestrian use, and we don't want anyone to get splashed by motorists. So again, we can use curb drains to get the water off the road quickly. Or a graded trench drain can also do this, perform the same function. One of the big drivers on every project, as we know, is cost. So precast curb drains and graded trench drains are ideal applications where curb inlet pits would otherwise be spaced closer together. So say at intervals of 20 metres or less. It's more expensive to install pit and pipe in these applications than a graded trench drain. So here's an example of a road project where the designers opted for closely spaced pits and pipe, where a continuous capture inlet system would have been more cost effective in this solution, as a solution. We actually carried out an install cost analysis of a curb inlet and pipe system compared to a precast graded trench drain and curb drain system. And the outcome was a graded trench drain was 15% cheaper than that of pit and pipe, and the curb drain was 36% cheaper. So really quite significant savings there. And finally, for road drainage design, precast channels can be installed on curbs. And this can be done by opening up a gap either on the inside or the outside edge of the channel for gentle curves on a large radius, or by grinding and mitering the channel units on site for tight curves and smaller radiuses. So here's for an example on an intersection widening and upgrade project where Telstra services were clashing with the pit and pipe design, and they designed and installed a shallow curve graded trench drain to act as a pipe to move the runoff around the corner and from the intersection to discharge into an existing curb inlet pit, which as an advantage avoided clashing with all the existing Telstra infrastructure or the need for costly relocation of these services. So now let's have a look at shared spaces and the important considerations to correctly specify and integrate a surface drainage system that is safe for both pedestrians and motorists. Shared spaces are increasingly transforming city centres, transport hubs, public domains into an inviting space where it's accessible for all users. And this is how Ausroads describes shared spaces or a shared zone. It reads, a shared zone is an area utilised by both pedestrians and vehicular traffic in which drivers must give way to pedestrians at all times, and where the street environment has been adapted for very low speed vehicles. Shared zones are normally used in these areas of high commercial activity, medium to high density residential areas or recreational areas. So, ideally, a shared space are located in areas with relatively flat pavements. The surface drainage needs to be designed with an appreciation of the grate slot size, the slip resistance consideration, the loading, the durability, and also must be accessible for safe passage for both pedestrians and also motorists. And so, of course, with any application of product, compliance with relevant legislation and standards is vital, will help solve many of these problems. When it comes to pedestrian safety for pavement elements, the requirements and the spread through a number of Australian standards because of the magnitude of factors that needs to be considered. So we'll look at some of those standards in detail shortly. But in addition to the Australian standards, many councils have their own planning regulations for external spaces, particularly when it comes to streetscapes. European or other standards are often referred or referenced as there's no application or applicable Australian standard to reference it against. So the following are some of the roads that are transformed into shared spaces. This is a before and after shot of Bank Street in Adelaide, which was transformed into a shared space where the speed was dropped to 10 kilometres an hour and the curbs were removed so people can move freely and share the space with vehicles and bicycles alike. Here in George Street, as we know, it's been converted into a shared zone with pedestrians, trams and vehicles accessing buildings. Flat space was created with the removal of curbs and gutters, graded trench drains specifically designed for tram drains. Were extensively used throughout the light rail corridor. Under Street in Canberra is a commercial and shopping precinct with shared zones created where vehicles give way to pedestrians at designated raised road crossings. So graded trench drains are used to outline the extent of the road and to intercept any runoff from the pedestrian areas. Here's a couple of Victorian projects where curb and gutters were removed and replaced with graded trench drains to allow pedestrians to move in all directions within that space. Here in South Australia, the graded trench drains incorporated nicely into the paved pedestrian-friendly areas that are accessible by motorists. And in Hobart Airport project, a traffical graded trench drain is used with different pavers and bollards to clearly segregate the shared zones and the pedestrian only. And a couple of Queensland examples of a shared space in an education precinct and a medium to high density residential area. Now let's have a look at some of the key factors to consider when designing a drainage system within a shared space. So here are 5 considerations when integrating drains into pavements to achieve those objectives of safety, form and function. And that's flat drainable surfaces, slot criteria, slip resistance, durability and strength, and access for maintenance. Then we'll discuss how drainage in shared spaces will integrate in with other transport modes, and also discuss hydraulic performance as it's also a critical factor. So bumpy or steep pedestrian spaces will create trip hazards, particularly for the elderly, children and those with a disability. Surface water management often leads designers to create steep pavements, but they can be designed flat if drainage is properly considered and incorporated during the planning phase. Graded trench drainage systems are continuous capture inlets with simple, constant grading on both sides of the drains. And as discussed earlier, precast drainage systems with a V-shaped channel profile have hydraulic advantages over U-shaped channels, in particular low flows with higher velocities. Channels are also available with built-in slopes and the inverted channel providing fall and if the surface and top of the grate is flat. So precast trench drainage systems are quick and easy to install, particularly compared to that of cast in situ trench drainage. The next element to consider are the slot sizes, because slot sizes are critical for pedestrian safety and should not hinder accessibility for wheelchairs and walking canes. New building works must be designed to comply with Disability Discrimination Act, and the DDA makes it against the law public spaces to be inaccessible for people with a disability. So slot sizes of grades will also determine how safe it is for cyclists and pedestrians wearing high heels or stilettos. AS 1428.1, designed for accessibility and mobility, was recently revised and released in 2021, and grades in paths of safe travel shall be in accordance with the following. Circular openings shall not be greater than 13 mil in diameter. Slotted openings shall not be greater than 13 mil and not greater than 150 mil, and be orientated so that the long dimension is transverse to that of the dominant direction of travel. And linear openings shall be orientated so the longer dimension is transverse to the dominant direction of travel, except where linear openings are less than 8 mm wide, and where linear openings are less than 8 mm wide, orientation is optional. We also need to consider bike safety, and is mandated by AS 3996, which takes into account the type of bar used in a grate and also the maximum slot dimensions to stop bicycle tyres getting wedged in the grate. However, heel safety is the most common complaints from users, and whilst there is no Australian standard for heel safety, there is an American standard that calls for slots less than 8 mm. But there is a trade-off here though between hydraulic intake and heel safety. So we don't want to see very narrow gaps, and whilst they are heel safe, they don't actually take the water away. And as a result, we tend to use a guideline of 10 mm. And as we know, there's been some famous people over the years that have been pictured getting their heels stuck in some grates. Slip resistance is becoming a massive concern for the Australian design community, and as litigation around these areas, the pressure is placed on the specifier to correctly specify all floor materials, including and to the standards. So in Australia, in comparison to the world, it really has a strong standard with AS 4586 with a supporting handbook of HB 198, which stipulates the minimum slip resistance for ratings for a variety of applications. So AS 4586 outlines the test methodologies to simulate different applications as a means to assess the slip resistance of a grate. So for grates, there's three main tests, either the oil wet ramp test, which is pictured on the top of the screen, for applications for industrial and commercial environments where there's likely to be oil on the floor, for example, commercial kitchens, and has a rating from R9 to 13, with 13 being the highest. Also, the wet barefoot test, which is designed for wet areas with bare feet, such as pools or change rooms. And this test has three categories of slip resistance, from A, B, and C, with C being the highest rating. And lastly, the wet pendulum test, which is most widely used test for slip resistance, as it's a portable test device and is generally used in litigation cases in situ testing. And this test is most suited for areas that get wet rain and traffic by worn heels and shared spaces for building entries, for example. And the rating is a rating from P0 to 5, with P5 being the highest rating. So it's actually the test that actually tests stormwater affected surfaces. Next is the loading, and considering the anticipated vehicle loads that a drain will be subjected to is critical, because underestimating this can lead to product failures, and overestimating it just adds more cost to the overall project. So it's an important design consideration. And load isn't just related to the physical load of the vehicle. We also have to consider the type and the speed of the vehicle, the wheel load, and how the vehicle will move on the grate, and the number of movements. There's also a couple of standards you need to be aware of when it comes to load classes. So AS 3996 is the Australian standard for access covers and grates, and this tells us how to test. How to test the load classification of the grate, but doesn't take into account of the underlying structure, so whether it be a trench drain or a drainage pit. However, EN 1433 is a European standard that tests both together. So we'd also test the drainage channel as well. This table also looks at load classes specified in AS 3996. It classifies applications from pedestrians from load class A all the way up to load class G, and shared spaces will fall into load class C, so for malls, pedestrian areas, open to slow moving traffic. And road drainage needs to be specified as load class D for major roads, freeways, shoulders, and loading docks. If the grates aren't locked into the channel, then it can damage both channel grate and loose grates. So a boltless locking system on grates, which allow quick and easy fitting and removal of the grates for maintenance and cleaning. The other option is bolted grates. With the risk of grates vibrating loose over time, it's common It's common to see that once bolts are removed during maintenance, they aren't often replaced, which can be a safety risk for users and road users. Slot drains are required discrete access points that help the designer to preserve the visual continuity of the pavement, and access points can be installed at the start or the end of every run, every 20 metres or so. The state governments all over the country investing billions of dollars into public transport. New metro lines and light rail projects are connecting communities from their space of residence to city centres, transport hubs, hospital, tertiary institutions and entertainment precincts, creating these shared spaces in and around each of these stations. Light rail systems have been established in many cities and new lines are constantly being designed and delivered. And light rail is so much more than metro lines because they run on the surface and are incorporated into shared spaces through high pedestrian traffic areas. So designers are often challenged to provide an effective drainage solution in very flat areas with the complexity of draining the track rail grooves. Specifically, designed tram drains will discharge the flow from the track rail groove through the holes that are drilled into the rail, into a chute connected to a drain and the pipe system. And these chutes are made from a rubber material and also used to isolate any stray current from the tracks, potentially making the grates live and hazardous to pedestrian users. And tram drain grates should be designed to take into consideration of the 5 key factors that we discussed earlier in the presentation. But it is absolutely critical when selecting a drainage system is the hydraulic performance and whether it will do the job that we need it to do. The hydraulic performance refers to the amount of water it can collect in a given time period, and that amount drives the product selection not only for the channel but also the grate, as the grate in some cases can be the restricting factor. And remember that undersized drainage systems can increase the risk of hazards and damage to property if the flow is not captured correctly, but conversely, an oversized system just adds unnecessary cost into a project. So as designers, how do we get that right? Well, if we consider the science behind channel hydraulics, the science behind the hydraulics of a trench is quite complicated, and there is many theories and equations to calculate it. But look, it is common for engineers to use a simple pipe or open channel formula, which is used to calculate drainage capacity. However, this assumes that the flow in the channel is uniform, and this might work for a culvert or a pipe, for example, where liquid is just moved from one end to the other. But non-uniform flow is a more accurate way to model trench hydraulics performance, particularly as it takes into consideration the collection of flow along the length of the trench drain, which can be used to plot the changing water profile and the depth of the trench drain. So beyond channels, the grade is also another consideration, and typically trench drains will reach, typically the trench drain itself will reach capacity before the grate, but I guess depending on the style of the grate, it may not be capable of capturing all of the flow, even if the channel is sized correctly. And grate failure is categorised by liquid bypassing of the grate as shown in the bottom image. Beyond the pure grate intake area, which is the open area of the grate, there are other factors that influence grate hydraulics, including the slot size, the slot orientation, the number of slots, and also any raised slip-resistant nodules also impact the orientation. The number of slots also raised slip-resistant nodules also interfere or can impact the flow of water, as they also slow the flow down and helps direct the water into the slots. And just lastly, just to touch on a little bit about ACCO, just in case you're hearing about us as a company for the first time today. ACCO Australia was established in the mid-1990s when ACCO bought Polycrete as an Australian precast drainage company. Over the years, ACCO has expanded beyond polymer concrete production, and we now manufacture stainless steel trench drains, rotationally moulded plastic pits, mild steel fabrication of access covers, all from our head office in Emu Plains, Western Sydney. So I just want to quickly run through ACO Brains. ACO Drain is our range of architectural and commercial linear drainage, manufactured from polymer concrete channels with an array of grades. ACO Infrastructure is our drainage channel specifically for heavy transportation and infrastructure applications. ACO Storm Bricks are modular underground stormwater storage tanks for retention, detention and infiltration. And ACO Access is a discrete range of access covers, and Cable Mate is our cable pit and cable ducting range. But just as important as the products, we can also help you as designers, and ACO can assist you with your next project. We have a do-it-yourself online program for designers to size up channel, and this is really helpful during the concept or prelim design phase to get quick answers on demand, whatever the time or day or night. So programs include Hydrolite, which is a trench hydraulic program used to help size up trench drain or check the performance of your trench drain design. GIC, or grading intake calculator, shows the performance of your preferred grade based on experimental test data. And whilst Hydrolite and GIC doesn't give you the full suite of documentation, it does help you give a quick indication of the hydraulic capacity of ACO's more popular trench drain products across 3 widths and 3 sloping system depth options. So another online program is also Scheduler, which is a program that can draw a simple trench drain or trench run and provide layouts, long sections, and also a bill of material to assist designers and contractors when it comes to procuring and also installation. Using the online hydraulic program will provide a good indication of the trench drain required, and to further refine your design, in particular during the detailed design stage, you can contact ACO's technical support team for ACO drain proposal with full hydraulic documentation, along with additional information to assist your specific specification, such as general installation details, spec clauses, drawings, and product information. And lastly, just to reiterate, we're here to help you across a broad range of projects with all our products. So askaco.com.au is how we capture all the services that we offer. So you can head into this site to access the channel hydraulic service, grade intake calculator, and design request forms, and so on. And also, our websites contain a lot of information and downloads to assist you with your next project. So thank you very much for listening today, and certainly look forward to your questions. Thank you.
Thank you to Alan and Darren for those great presentations, particularly as water and storms and floods have been so topical over recent weeks in a lot of the country. It's now your turn to get involved. Please ask our questions, speakers' questions, via the chat box. And if you could put down who your question is directed to. Also, a big thank you for everyone who submitted questions whilst registering. And I'd like to take the opportunity of welcoming Darren Chan, who's Brand Manager for Civil Construction Products at ACO, and who is joining today's Q&A session. So without further ado, I might start off with a question for you, Alan. And the questions come in from Sujatha, who's in New South Wales. Good afternoon to you, asking, are the current drainage systems in cities adequate, especially considering the impact of climate change and global warming? Great question. Alan.
Hi, thanks for that question. The short answer is no. As towns develop into cities, they're often designed for smaller rainfall events when they're first being built, and then over time standards can change. You can also get further land development putting additional pressure on the original system. On top of that, you've got to consider increasing rainfall intensities from climate change. So they're kind of shot from square one. And you need to consider some more creative solutions, because you either need to increase the capacity of the existing system underground in the city or attenuate flows before it gets to the system to keep them working. To be honest, it's a little bit beyond this webinar. There's scope just in that one question for an entire additional webinar.
Thanks, Alan, and maybe that's something we should take note of. And just staying with you and also staying in New South Wales, we've had a question come in from Mario who's asking, given the change in storm downpours of late, is it wise to still be using 1 in 100 runoff? And also how to update AS3500? Thanks, Mario. Alan.
So AS3500 is obviously continually being reviewed and updated. It's going to be hard to say if any one part is in particular need of being updated at present. But if Mario has an area that he thinks needs to be worked on, I'd be interested to hear about it, and I can answer that specifically. The 1 in 100 it's a very common question. The one of the leading flood designers at Arup actually commented that in an 80-year lifespan, you should expect there's about a 19% chance of seeing at least 2 1 in 100 or 1% AEP events in your life. So they're not 1 in 100. They turn up once every 100 years. The rainfall patterns they use statistical probabilities over long time scales. So we might get 3 or 4 years that are very, very wet and then have a decade where it doesn't rain at all, at which point normally we're being told your drainage is too big, it's over the top, you're not doing it right. And then as soon as it's raining, you've not designed it to be sufficiently large. Designing for larger return periods, it costs more. It can potentially cause more maintenance issues because you're trying to capture a big flow for your design storm, and then the self-cleansing small storm will not be able to self-cleanse. So it's probably more important to consider the consequence of your system overtopping. If there's somewhere safe for that flow to go beyond whatever design you're designing for, then you don't need to design it for more than that. And then just make sure that the end client understands and accepts what you're designing and what will happen beyond that design.
Thanks, Alan, for that. Over to you, Greg, and also this question's been directed to you first to Greg and then to Alan. And the question's coming from John asking, should all drainage structures in flood-prone areas have a design for failure contingency plan? And where does the water go when the drainage structure fails? Thanks, John, for that. Greg.
Yeah, thank you, John, for that question. Look, any trench drainage system is designed for a set of parameters, I guess. So for a set area with a given liquid over a certain period of time, we would design that for that channel to sufficiently drain that amount of liquid. We do often get asked, can we factor in a blockage factor on gratings, for example? So any calculations that we might run would be based on clear flow. But we do know that from time to time the gratings can be blocked. So we've often been asked to allow for a blockage factor. But again, I think it's important, and we touched on it, that you don't want to have drains that are too wide either. So what's the parameter for failure? Over 1 in 100 or greater. And some of the storm events we've seen have been, biblical has been some of the description of some of the past events. So how do you plan for that? So I think it's important for the predominant scope that trench drains are designed to sufficiently drain away the liquid without being over-designed, because as we spoke about on those normal events or smaller events, then if the drain is too wide, you're not going to have sufficient flow, and then can cause siltation and additional issues. And where it would flow, well, it depends on what the grade of the surface level is. So where it drains either downstream or into footpaths or into buildings or whatever the case may be in the surrounding areas. Do you want to add anything to that, Alan?
Yeah, I think you've covered a lot of it. Drainage structures, not just in flood-prone areas, all drainage needs to have this consideration. It's why we look at a minor storm and a major storm. So we design for that minor storm, make sure that the system is going to work, and then look where the flows will go in a bigger major storm that exceeds that. And generally, you want that overland flow path to take it away to somewhere, to a creek, ideally, or to the ocean. Where there isn't that option because you've got a trapped low point and it would go into a building, then you upsize the the network both capture and pipe size to take the flow away. That's, again, there's a limit. You can't design for everything without having a system that's excessively big and will break.
Thanks, Alan and Greg. Just bringing Darren into the discussion, we've had a question come in from Theodorus, who's in Victoria, asking you, Darren, has echo inflow capacities for each grate?
Yeah, Echo has invested in a lot of money in getting test results for our grates. So a lot of we've got the biggest range of variety of grates for our commercial systems. And what we did was we engaged the University of New South Wales at the Water Research Lab at Manlyvale, and they tested our grates on a ramp. The ramp was able to be inclined to certain different crossfalls from 0.5% up to 9%. And what we're able to do is determine the actual intake capacity of each grate just prior to it bypassing the grate. So whether the water will skip across the grate, bypass is what we sort of is classified as our capacity, and we have a range of data on all our grates that we sell, and we've also invested in a software program that is accessible by engineers, which is our GIG program. If you go to our website, you can put in your catchment flows, your lengths, other details, your rainfall intensities, and then we can determine what the grate you prefer is, I suppose, the efficiency of that grate, or if it's at capacity. And we can provide that online. Also, we can provide that information for our technical support team too. So that's available. But yeah, please come and ask Echo, and we can give you that information, definitely.
Thanks for that, Darren. And moving up the country to Queensland, we've had a question that's coming from Reese, asking you, Greg, and also Alan. Reese is saying, the biggest issue I've found with trench drainage systems is the frequency with which they get blocked and become worthless. Other than regular sweeping or similar, are there any innovative ways to ensure these systems work but with minimal maintenance? Greg, your thoughts?
Yes, look, thank you for that question. It's a question that gets asked often. So I guess there's two things for that. One at sort of surface level, and also subsurface with the trench drain itself. So at surface level, and again, it certainly depends on the location. So if we're talking, say, a road carriageway that's not in a pedestrian space, certainly use a high flow grate, or grates that have large apertures, because any debris at surface level again can fall through the grate, and that's typically what we see used on a lot of road carriageways, for example. Having said that, also in some of those pedestrian areas, so on a median, and there's a pedestrian crossing, that in that location, just in that location where the pedestrians cross, we would use a pedestrian style grate, but predominantly 90% of the system is a high flow or large aperture grate. So that's the first thing. If there is a requirement for, say, pedestrian throughout the whole pedestrian requirement throughout the entire system, then there certainly would be some maintenance regime that would be required. Just very quickly, in terms of a subsurface or in the channel itself, look, V-shaped profile channels, better from a velocity point of view, reducing siltation, adding slope within the system, or selecting slope systems wherever you can, creates more velocity, and then moves some of the siltation as well through the channel system, and also importantly having sufficient flow. So like we mentioned earlier, not over designing it, so then creating low flows within the system. So we would always suggest wherever you can use slope systems will be an advantage. And there's next to very minimal cost, just a little bit of extra concrete, but providing you've got the space to install it, then absolutely use slope channels wherever you can. Alan?
Thanks, Greg. Alan, have you anything to add?
Yeah, so we covered a bit of this in the presentation, so making sure you're using it as narrow a channel as possible, putting it on a slope. In terms of innovative solutions, I did touch on this as well. If it's near a building and you connect a roof water downpipe, that can put that push of flow in at the top of the trench and keep things flowing. You could also consider, if there's a water main nearby, just connecting into that. So the maintenance team could literally turn on a tap, flush the trench, turn the tap off. It's a bit of extra cost, but it would significantly reduce the maintenance burden that would be on them.
Thanks, Alan. Back to you, Greg. We've had an interesting question coming from Nicholas, who's in New South Wales. Good afternoon to you. Talking about the rail environment, asking you, Greg, what solutions do you have for the rail environment? Thanks, Nicholas.
Yeah, thanks for that question. And I guess it depends on what you term in the rail environment. We're talking about large rail and passenger rail, and certainly on platform drainage, for example. Absolutely, it's important to have surface drainage systems that carry not only a hill safe requirement, also slip resistance requirement to make sure it meets the pedestrian requirement, and particularly in terms of accessibility and mobility as well. But then also, it's important, like any system, it's generally the asset holder that has to undertake any maintenance. So you're looking for systems that not only meet the user requirements, as I just spoke about, but also the gratings can be fitted and removed easily, but fitted from a security point of view, and locked, but can be removed to enable any maintenance that may need to be carried out. So I think that's an important aspect to consider. If we're looking at light rail, and we've undertaken a number of light rail projects recently in Australia, there is very specific drains for light rail in terms of tram drain. So these are drains that are specifically designed to fit within the gauge of the rail. They have neoprene chutes to isolate that drain from the rail and reduce any issues of stray current. But those chutes on either side enable the gauge to be drained, so there'll be a slot within the gauge rail itself, which allows in the drainage to the channel, but also at the same time, those channels can carry a pedestrian safe rate as well. So it meets the user requirements, but then also meets hydraulic requirements of the site.
Thanks, Greg. And we've had a great question that's coming. Yeah, we've had a great question that's coming from Christopher, who's in Queensland, and this is direct to you, Alan, asking, what are some of the ways that we can overcome council/government's hesitation with using trench drains? Alan?
Yeah, this one's difficult. We've mentioned it a few times. If you're putting in poorly thought out trenches, then they're installed and they become worthless and full of sediment, or they become a maintenance liability. And the more often we do that, the more resistance there will be, which is probably fair enough, to using them. So when they are needed and it's the right option to put it in, and as a designer, you believe that this is the right option, you need to go back to stakeholder engagement. You've got to sit down and talk to the client, not just the project manager, but their maintenance team, and get everyone to agree that this is the right solution and that you've understood the issues, and put forward some solutions. Because if you put in something and say, yes, you'll need to clean it out every year, every 6 months, then that's not the solution and you shouldn't be putting it in. But equally, if you've got something that you can demonstrate it will clean itself, it won't need to be heavily maintained, then you need to be communicating that to everyone so that everyone agrees this is the right solution. And to do that, you may actually need to show the alternative design with, we'll need this many pits, or we'll have a flow width that is this wide if we don't put this in, to get the agreement that, okay, it's worth putting it in, and maybe you relax the standards so you have a smaller design storm, which means it's easier to self-cleanse the trench.
Thanks, Alan. And we've had quite a few questions around climate change, but I'm sort of interested in Henry's question in New South Wales, direct to Alan. But he's asking, actually, the panel is, how confident is the panel that we as professional engineers can effectively take climate change into account in designs. So Alan, do you want to kick off?
Sure. With sufficient knowledge, which I think at this point we do have, we should be very confident. We can already design to allow for sea level rise or increased rainfall. And quite often that's actually included in the requirements for the project, that you include that in your design from day one. If it's not included, then it's our duty as a professional designer to recommend adding that in so the client can understand why it's in, what the difference is between having it in and not having it in. And to be honest, if you step back and look at this, it makes a big difference for things like bridge levels and culvert sizes, but pit and pipe networks, it generally falls out as maybe 1 or 2 extra inlets and a pipe here or there that goes up a size. So it's not difficult to include it into the design, and it future-proofs us quite well.
Thanks. Greg, do you want to add to that from a manufacturer perspective?
Yeah, I think Alan's pretty well covered it, and yeah, I totally agree. Yeah, pretty confident. We get asked, well, from what we get asked from a designer side often is to make sure that the calculations that are run are based on the ongoing increase of stormwater events and rainfall events. Absolutely, and often we get asked to account for a number of factors. So it could be a minor storm event, but then also run some of those calculations for a major storm event to try and take some of those considerations into fact and how it's going to perform under those conditions. So yeah, agree, pretty confident.
Thanks, Greg. And Darren, we've had a question that's come in from Di. Good afternoon, Di. And she's saying, hi, Darren, as more services are diverted to being underground, this will become more of an issue for future generations. This is also a significant issue when replacing poles on the network. Would you like to comment on what Di is saying?
I suppose with a lot of development now, we're developing in new areas that all the services are putting underground. But if we're working in built-up areas already, there is also services in the ground. That's why continuous capture inlet systems are, as Alan alluded to, are shallow systems. They're usually not more than half a metre deep. And with all the services in the ground, if it's power, whether it's power, sewer, they're usually over 600 deep. And with designing for trench or designing drainage, if we're trying to widen a road, put a extended right-hand turn bays in, where we're trying to put it into a smaller space, and then there will become a lot of clashes with these existing services. So the benefit of using continuous capture inlets such as trench drains and curb drains, they're shallow excavation. They take up a space that is above all these services, and you won't be having these clashes or having to move these or move the services, which can be very costly. So yeah, the continuous capture inlets is a solution when it comes to this.
Thanks for that. And back over to you, Alan. We've had a question that's come in from Rob asking, what about detention/retention ponds for sediment? Thanks, Alan.
So I wonder if this came in looking at one of those last pictures I had up. There was a bioretention pond at the edge of a road, and it had a little sediment forebase. So sediment is needed, and if you are putting in something to detain or retain stormwater, you obviously don't want the sediment to be in there because it'll kill the plants if it's planted, or it will fill the tank up if it's not. The solution is just to design somewhere for it to go. So bioretention basins best practice includes a pre-sediment forebay, which allows the main coarse sediments to settle out and be easily collected and removed. And that keeps your detention or retention area clear of the sediment.
Thanks, Alan, for that. And just staying with you for now, we've had a question that's come in from Hilton. Good afternoon to you, asking Alan, does designing urban drainage for a 5 or 10-year recurrence interval effectively mean that for most events, the capacity of the drainage system will be exceeded? What RI do you recommend? Thanks, Alan.
No, it won't be exceeded. The clue is in the name there. If you design for a 5-year or 10-year, so that's a 10% or 18% AEP, then the majority of storms that happen will be captured by the storm, by the system. And it's only the larger, less frequent events, which unfortunately are the ones that will stick in everyone's mind, that will get captured, that will overtop the system. Yeah, so I think a 5 or 10 is perfectly adequate. If you try and design for something bigger, then in the smaller events, you'll get sediment settling out, and then the whole system won't work.
Thanks for that. And Greg, we've had a question from Shane in Queensland who's asking you, how is inlet capacity calculated?
Yeah, thank you, Shane. And we touched on this a little bit earlier. So look, there's a number of methodologies, either from a weir flow equation or ground orifice. All of our grates have been tested at the University of New South Wales using a number of those test methodologies. So by getting onto the askacco.com.au website, you can actually input the required parameters when you select the grate, and we'll actually tell you how the grates will perform under those specific conditions. That way you know that it's going to have sufficient intake of the grates.
Thanks, Greg. And we've had a question that's coming from Helen. Helen's in Queensland. And Alan, Helen's asking you, in terms of design, should we be considering condition probabilities of exceedance? For example, extracting the probabilities in La Nina clustered periods. Your thoughts, Alan?
To a certain extent, yes, and I think we already do, noting that individual rainfall events are averaged over a long period of time. But in terms of conditional probabilities, that shouldn't mean that we design, for example, a pit and pipe drainage network for a 10% AEP storm and use a 10% AEP flood at the outlet. The exact probability of an event like that will be related to the characteristics of the river and catchment, but it will be closer to a 1% AEP event than the 10% AEP event you're designing for. As an example, remember in 2011 when Brisbane was flooding, but it was dry and sunny. So the local catchment storm was entirely disconnected from the river flood. And the recent floods in Brisbane had rainfall totals closer to a 0.1% AEP event. So it's more appropriate when you're looking at conditional probability to consider a suite of storms. For example, you could look at a 10% AEP storm for your pit and pipe network, combined with a 1 exceedance per year flood level, and then a 1 exceedance per year local storm with a 10% flood level, and then put the two together and use an 18% AEP storm with a half a year exceedance flood level to assess different events with a similar 10% AEP of occurring together.
Thanks, Alan. And we're sort of running out of time, as always we do. And we talked a lot about heel-safe grates in the presentations, Greg. But maybe just circling back to that and sort of summarising on that, Robert in Queensland is asking you, can you explain the requirements for heel-safe grates within car parks, staff car park or shopping centre, where there is potential for incidental pedestrian traffic? Thank you, Greg.
Yeah, thank you. And one of the design considerations on any project is taking into account all the scenarios. And often it's the incidental scenarios that are often missed. So, i.e., we didn't think pedestrians were going to traverse or access that area, and therefore you have an issue where someone has a heel stuck, and or you have trips and falls. So certainly it's important to account for all the scenarios. If it is likely to have pedestrians through there, then you need to select pedestrian friendly grates, whether that be heel safe, which is generally 10 mil or less. And remember, in Australia, there is no Australian standard for heel safe. Generally 10 mil or less is the referred to requirement. So it's important to make sure that it meets that, but also the accessibility and mobility code as well. And also, while we're highlighting pedestrians, the grates need to be bike safe, and also any intended loads. But from a pedestrian point of view, if you think there's going to be pedestrian traffic, then you need to allow for that and select a pedestrian friendly grate.
Thanks. Thank you for that, Greg. And we have had lots of questions. And as always, we haven't had time to get to them all. But if you did give permission to share your details, then we will get back to you with some answers. That's all we have time for today. Please join me once again in thanking Alan Roxy, Greg Facey and Darren Chan for their time. I'd also like to thank Engineers Australia's long-standing industry partner, ECHO, for their support. Please, as always, if you could complete a short feedback form, which is linked in the description box below, helps us improve and plan for future sessions. Just quickly, I'd like to let you know that the Australian Excellence Awards nominations are now open, people and projects, and the nomination website with further information is linked in the description box. Thank you again for joining us, and we hope to see you at our next Thought Leaders event. Thank you and good afternoon.